So, that being said, it's a good motivation to start early. And I wish I started earlier than I did in college, and I'm challenging you guys to capitalize on that now.
Hey, you want to learn about electricity?
In order to understand just about anything today, you must first understand what electricity is. We all have a rough idea of what electricity is based on practical experience. Some of these might include, we know that electricity flows through wires. We know that electricity comes from power plants that burn coal, catch the wind, or harness nuclear reactions. We know that electricity travels from power plants to our homes in big cables and comes in our houses so that we can use our outlets. We know that electricity can be stored in batteries, so when batteries die, their electricity is gone. We know that there are volts, watts, and amps that measure electricity, but do we really understand what those mean? Let's start here with the basics.
All right, so Tosin, what's your full name?
So my full name is Oluwatosin Akinsanya.
So what's your background? Where did you grow up?
So I'm originally from Nigeria. I was born and raised 13 years. I moved to the United States in 2011. I went through a high school year as well. I started high school in Nigeria, but my age and everything sort of made me start over when I got to America. And then I went to community college and transferred to University of Illinois at Urbana-Champaign to study electrical engineering with a focus in power systems.
The fundamental laws of electricity are mathematically complex, but using water as an analogy offers an easy way to gain a basic understanding. There are three basic components of electricity. First is current, which is measured in amps and defines the flow of electricity. You can think of current as the water flowing through a pipe. Second is resistance, which is measured in ohms. You can think of resistance like a valve that slows down the water flow in a pipe, similar to a dimmer switch in your house that limits the brightness of your lights, but instead limits the water flowing through the pipe. The third is voltage, which is measured in volts. This is the amount of force required to push a current through a resistance. You can think of voltage like the pressure that pushes water through a pipe.
Did you know that Jerry Lawson was a self-taught electronics engineer who developed the first commercially viable video game cartridge for the Fairchild Channel F console? He is known as the father of modern gaming.
The main electrical law that you may have heard of is called Ohm's law. Voltage, current, and resistance are all related according to Ohm's law, which states that voltage equals current times resistance. Anything that you plug in and draws electrical current is called an electrical load, and these are basically the resistors in the Ohm's law equation. For a constant voltage level, if you reduce the resistance, you get more current or flow. The voltage in your house is relatively constant, about 120 volts. So for a big electrical load like a microwave, you would have a lot more current flow. For a small load like an LED light bulb, you would have a very small current flow. As an example, take a hairdryer plugged into a 120 volt outlet that uses 12.5 amps of current. What would the resistance be? Well, according to Ohm's law, resistance equals voltage divided by current, or 120 volts divided by 12.5 amps, which equals 9.6 ohms. To demonstrate Ohm's law, we have this demonstration here. So here is my voltage source, which can be considered as my power source. Right here is a valve, which you can think of as a resistor. Since the valve is closed, this means that this is a big resistor. And if I open this valve or reduce my resistance, this creates a large current flow. And the more I close it, or the more I increase my resistance, you can notice how the water flow or the current is less. So now you understand Ohm's law, which is not that complicated. An important term to understand is power. And sticking to the water analogy, you can think of power as the volume of water that is flowing in the pipe. Electric power is measured in watts, and larger systems are measured in kilowatts, which is equal to 1,000 watts, or megawatts, which is equal to 1 million watts. So for the same hairdryer, you could calculate how much power it uses two different ways. In this case, the voltage times current is equal to power, or watts, which would be 120 volts times 12.5 amps, which would equal 1,500 watts. Also, you could calculate watts by taking current squared times resistance, or 12.5 squared times 9.6, which also equals 1,500 watts. You may have also heard the term watts when you're talking about light bulbs, especially the old kind referred to as incandescent light bulbs, which might be rated 25, 75, or 100 watts. You might see an LED light that has over a 10 watt rating, but compared to a 75 watt equivalent of an incandescent light bulb. An important term related to power is energy, which is like measuring the volume of water that has flowed through the pipe over a period of time. Electric energy is often confused with electric power, but they are different. Power measures capacity, and energy measures delivery. Electric energy is measured in kilowatt hours. If your parents replaced 10 100-watt light bulbs with new LED lights that only use 10 watts each, they would save 900 watts anytime the lights are on and would still get the same amount of light. If your lights are on for 10 hours every day, then this would save 9,000 watt hours, or 9 kilowatt hours of energy per day. At 10 cents per kilowatt hour, that would be 90 cents per day, or $27 per month savings on your electric bill. These savings are just for 10 light bulbs only. Imagine what a whole neighborhood of houses could save just by changing over to LED light bulbs.
So how was high school? Definitely as like an immigrant from Nigeria, was that interesting for you? Good, bad?
It was. High school was definitely interesting. It was a lot of culture shock too as well. I didn't know how to speak English fluently. I spoke pidgin English, so it was really hard to communicate with people, especially my teachers, and really comprehend the material. To the point I'm able to take a test and pass them. But I had really good people. I had a good network and I had a good support system that sort of helped guide me. I was part of Chicago Scholars Umoja Corporation that literally helped fund my high school, as well as helping me get scholarship opportunities for college and things like that. So I had a really good network that sort of helped smooth out the way out, especially my junior and senior year in high school.
Have you ever heard of the war of currents or wondered why our outlets are rated at 120 volts? Or why your laptop or phone charger has this big block on it? Well, to start, you first need to understand the difference between direct current and alternating current. Direct current, or DC, means the electrical current flows in one direction, possessing a voltage with constant polarity, either negative or positive. Think of a battery, where the current passes from the positive terminal to the negative terminal. You can think of DC current like the normal flow of water in a pipe, or think about batteries in a flashlight. Maybe you've done some experiments in school where you hooked up a light bulb to a battery. Another type of current is alternating current, which means that the current changes directions, which changes the polarity of the voltages over time. You can think of AC current like the water flowing back and forth in a pipe many times per second, faster than your eyes can see, so it looks like it's continuous.
One of the most important discoveries was made by Faraday. He found that when he moved a magnet in a coil of wire, it generated a current in that wire. That current was actually a direct current, or DC.
Tesla found that if you oscillate the magnet back and forth, an alternating current flows in the wire, or AC. This is the basic operating principle of a generator. In a generator, a magnetized rotor spins inside a stator, creating electric power. The energy input to spin the rotor can come from coal, natural gas, and nuclear. And of course, interns.
Modern-day ellipticals and exercise bikes use a similar type of generator to power the onboard electronics. So if you're paying for a gym membership, you're basically paying to produce electricity. A wise man once said, if you don't want to pay your electric bill, hook up an elliptical to your house and feel the burn.
Motors are physically the same as generators. Just like generators, a magnetic rotor spins inside the energized stator. However, in this case, electrical energy is fed to the stator, creating a magnetic field, which causes the physical rotation of the rotor.
Have you talked about a sinusoidal or sine wave in school? If not, you will, and this might help you understand what AC waveforms look like. In the US, our electrical system oscillates at 60 times per second, or 60 hertz. This means that AC power completes 60 cycles of sine waves every second. The human eye is able to see these cycle changes at any frequency below 20 hertz. Let's take this demonstration with a light bulb and a power source. If I set the frequency to 16 hertz, you would see all the lights in your house flicker like this consistently 16 times per second. The higher I make the frequency, the faster the cycles are, and the closer I get to 60 hertz, the less the human eye can see these flickers. This is why you don't get dizzy on a daily basis when your lights are on.
So is this your first time in the Pittsburgh area?
Yeah, pretty much. Oh, actually, I've been in Pittsburgh for a conference before for the National Society of Black Engineers. So I was here for their regional fall conference. That's what it's called. Yeah.
You get French fries on championship?
Yeah. Yes, I've seen people do that. That's interesting. Yeah.
Now on to a quick history lesson to help you understand why our power grid runs on AC power instead of DC. In the late 1800s, Thomas Edison, who invented the light bulb, developed DC motors to power homes, businesses, and entire cities. However, he was quickly presented with a serious issue that DC could not be converted to higher or lower voltages, making it more difficult to transfer electricity reliably over long distances. Meanwhile, Nikola Tesla and George Westinghouse campaigned against DC and developed the AC system using relatively inexpensive transformers, which allowed them the ability to transport power over long distances by changing the voltage levels. Tesla then invented a motor which was able to be used on the AC system and essentially confirmed AC to be the winner of the current war. Tesla and Westinghouse championed AC over DC, and now AC is the global standard for delivering electricity to homes and buildings via the grid. Interestingly, most of the things you use in your house today, like your phone charger, computer battery, convert AC back to DC, so maybe we are going back to the other way to Edison's original plan. Fun fact, African-American inventor Louis Latimer was instrumental in helping Edison develop the incandescent light bulb. He drew the first electric light blueprints and patented the method for making carbon filaments, allowing light bulbs to burn for hours instead of minutes, which made electric lighting more practical and affordable for the average household.
The other advice I'll say is just to make sure that you're connected with people that that can help sustain you through like college and through your high school career. I feel like one of the biggest reasons I'm literally in Eaton today is because I had mentors, I had people that helped me, build up my confidence, my self-esteem, to be able to talk about, things, and just were patient with me to be able to teach me things. I'm not a fast learner. I'm not somebody that just grab things like that, but when I do grab it, I hold on to it for a very long time. So teachers and mentors matter to me a lot. Just trying to find people that you could really sit down and be open and transparent with, and they can be open and transparent with you too.
So how does this relate to us? Well, every day we're surrounded by one of the most important innovations of all time, electricity. We're so dependent on electricity that it's extremely difficult to imagine living without it. Although humans have survived for centuries, the chances of the human race thriving without electricity today is highly unlikely. Starting with your house, All appliances, entertainment, lighting, and all technology depend on electricity. Traveling with electric trains, airplanes, and even some cars would not be possible without electricity. Medical facilities especially depend on electricity for X-ray abilities, computers, monitoring systems, and many more. Without electricity, hospitals and medicine would not be able to advance and cure illnesses. Electric power is something that we use every single day and is often taken for granted. Many of us do not take the time to understand how we get electricity to power our lights when we flick that switch. In fact, many of us do not even realize how dependent we are on electricity until we don't have it anymore. I'm sure many of you have experienced some sort of electrical outage from a storm or snow blizzard and panicked when the electricity went out. Since we can't see electrical current, it's not obvious to the average person what's happening. That's why for any career you go into, it's important to understand the basics of electricity and how it works.
Hi, I'm Amber Wright, and I'm actually an electrical engineer from the University of Pittsburgh, and I graduated in 2012. I actually, spent quite a bit of my time while in school doing internships and co-ops and various experiences that you can get in almost any industry, before you actually have your degree. And so, I challenge every single one of you guys to do the same thing. Right now, I know you have an interest. Go after that interest. Find a certificate or a program that matches that interest today and get some experience in that industry. You might find out that it's the direction that you want to go, or you might find out it's simply just an interest. With that being said, it's a good motivation to start early. And I wish I started earlier than I did in college, and I'm challenging you guys to capitalize on that now. So, once I graduated Eaton, I went through a rotational program that was for application engineers, and what it did is it gave me multiple experiences throughout the organization that I worked for. I did about 13 jobs in the course of 3 years, and that gave me a skill set that's hard to match. Going STEM is really an opportunity to diversify and differentiate yourself from the competitive landscape out there. The skills that you learn in STEM are hard to learn without going through those type of rigorous programs. And so it doesn't mean that you have to get your degree and go straight into an industry that ties you to that degree. It just means that you've proven yourself, especially like an engineering program or a science program, that you're willing to fight that battle of doing hard problem solving skills and really producing something that society needs and contributing in a bigger way. So I challenge you to, consider going into a STEM role or STEM program to see if it's something that slightly, interests you, but also remember that you could at any point change direction and use the same skill sets that you've learned in a STEM program in almost any industry. So good luck, guys, and thanks for including me.